Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, today our third lesson of this chapter, 3.1.3, is going to continue working with the idea of finding a pattern in the with the tile patterns and being able to create a rule based on noticing the patterns. And we're going to take a look at one of the tools that you have available to you in your online book. I'll just go ahead and pull this up right now so you can see. So when you go to your online book, we go to chapter 3.1.3. You can see here's the beginning of the chapter. I'm going to tell you right now, the resource page or the e-tools that they have for this particular lesson, not the easiest to work with. Like this guy right here is going to help us with one of the problems, and I guess those are supposed to be like different parts that we're supposed to be able to take off. Not quite sure exactly how this works. But there is something on here that I do want you to pay attention to. If not the e-tools that they have provided, I'm going to show you how to just go up and use, just in general, the Desmos graphing calculator. Okay, so I'm going to go ahead and open this up, and you're going to see here's a graph over here, and here's an opportunity for you to add an item. You can either create a table, or you can just create a rule in here. We'll get there in a second, or a few minutes, I should say, once we get to that portion of the lesson. So once again, I'm going to close out of this so that you'll be able to see from the very beginning, once we start going to a particular problem, how you can use the calculators on your online book to do some different work that's going to help you with your graphing. Okay, so let's go back to the lesson and get into it. All right, so in the last two lessons, you examined several patterns. You learned how to represent the pattern in a table and with a rule. We also, I think, did a little graphing. For the next few days, you will learn a powerful new way to represent a pattern and make predictions. As you work with your team or on your own watching this video, use these focus questions to help direct your thinking. What is the rule, and how can you represent the pattern? Okay, so this particular problem, problem 18, is called the Big C. And I'm going to attach, you should see this resource page on the classroom, and you can print it off if you want, or if you've got graph paper, you can just draw these and just reproduce them on your graph paper. So here you got figure 1, figure 2, and figure 3. See how they're forming a big C there? Notice the patterns or the trends to go from figure 1 to figure 2 and from figure 2 to figure 3. Where do you see the growth happening? And what we're going to do is we're going to create an XY table, the table of values, to show that growth. We're going to try and determine what the rule would be. Then we're going to graph it, okay? And what I want to show you is how you can use that online graphing calculator that I showed you here, the Desmos graphing calculator, to help determine if your rule is correct, okay? So let's go ahead and get started. What is it we're going to have to do? How many tiles will figure 5 have? Justify your answer in at least 2 different ways, okay? And then what will figure 100 look like, and how really let's just focus on how many tiles will it have and how can you be sure. Okay, so what I'd like for you to do is either use that resource page and build your figure 0 and your figure 4, and then once you figure out what that pattern is, then use that to answer the question on the previous page of how many tiles will be in figure 5. Fill in this table completely before you do that, and then let's see if we can, well, then we can graph it. That's what we would do next, is we would graph this, and I'll show you how to graph it on the Desmos calculator just using the points from your table, and then we'll see if we can play that silent board game kind of a strategy to figure out what the rule would be. Remembering that our figure number for your in, these are your x values, and your number of tiles will be your y values. Okay, so let's go ahead and pause and go ahead and look for the pattern of growth. Where do you see the growth happening between figure 1, figure 2, and figure 3? Continue that pattern to make figure 4, and then work your way backward to make figure 0. Then count the number of tiles in each one and put those into a table. And once you've done that, then go ahead and pause. If you want to go ahead and graph everything as well, you can. But if you want to pause it or unpause, and then I'll show you how to create the graph on the Desmos calculator and then transfer that information onto this. And then we'll see about finding the rule. Okay? So go ahead and pause. I'm going to pause as well because I'm going to do the work too. All right. Let's do our analysis here. First off, I'm going to count how many tiles are in figure 1. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I suppose we can go ahead and do the reveal for figure 1. Should have 9. And then for figure 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that increased by 6, right? So where does it look like it increased by 6? It looks like here, well, yeah, here's an add-on, here's an add-on, here's an add-on, here's an add-on. It looks like you had one in the middle there, and now you've got a couple there. So let's move on to this one. See if this one increases by 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So did that add on 6 as well, 15 to 21? Yeah. And so here you've got the same situation where you got 2 added on here, you got 2 added on here, and then you added 1 there, and you added 1 there. So it's kind of like you're lifting this part up a little bit, taking this part down a little bit, and inserting these 2 guys in there to make that inner column. And then here you've got a block of 2 added on the top and a matching block of 2 there. So if I take this shape and I add, let me go ahead and get rid, nope. Let me get rid of these markings. If I were to add another 2 here, add another 2 here, that would make these 4 rows of 5, 2 on the top, 2 on the bottom, and then I'd have to lift this up and put another tile in there and push that one down and put another tile there. And so this is what my figure 4 looked like. We got 10, 20, 21, 22, 23, 24, 25, 26, 27. Is that an increase of 6? Yes, it is. Okay, so we've got a consistent growth pattern where every figure number is increasing by 6. So I believe in that pattern, the 5th figure should then have 33, which is going to be an answer to the question on the previous page. And now when we're working backwards, this had 9. So if you take away 6 from the 9, you end up with 3. Now the question is, where would that 3 go? So let's go ahead and erase these guys. And let's think of our pattern of growth. We would take those guys away and scrunch them together to make your 1, 2, 3, 4, right? 1, 2, 3, 4, 4 here, and then just 1 in the middle. So that means I'm going to now take away this one, take away this one, and this one, and then in the middle, we took away that, and we took away this, and then scrunched them together. So you got your 1, 2, and your 3, which I put together like this. Now, I've seen some students that have drawn figure 0 like this, but I feel like as you were increasing, you would lift up the top, push on the bottom, and insert a couple. And so I figure that's probably what we're doing here. So it started off like this before we pushed them apart and started adding those tiles in the middle and then building off of that top and bottom part of the seat. So I believe this is what figure 0 would look like, and that for sure has 3 tiles in it. Okay. So now let's go to our Desmos calculator and I'll show you how this works. We're going to go to a decimals graphing calculator. And you can use this all the time. You know, this online tool is available. It doesn't matter what lesson you're in. We could be in lesson 2, chapter 2. Come on, chapter 2. See how it's still there? I go to lesson 2.1.3, which has nothing to do with what we're doing here, but those calculators are still there. That is always going to be at the top, no matter what lesson you're working through. So as we go through the book, and you find a need to do graphing, you can always access these graphing calculators. So Desmos calculator, now you see that plus sign there? If you click on that, this gives you the option. Do you want to create a table? Let's go ahead and do that. So we have a table of values here. Let's go ahead and put in all of these ordered pairs. What do we have? 0, 3, 1, 9, 2, 15. So I'm going to put in 0, 3. You see how it shows up on the graph, the point? Let's go to the next one, would be 1, 9. You see how that shows up? And then we go to the next one, we have 2, 15, and you might be looking at that and saying, well, I can't see everything, right? Well, okay, let's go ahead and pan out a little bit, and we'll be able to see them a little bit more. So it's changing the scaling of your X and your Y axis, so that'll show up a little bit better. Maybe we don't need it that far out. What was the next one? The next one was 321. That fits in there. Is it forming a straight line? That's what we want, correct? And we had 427. And let's go ahead and put in the 533. Okay, so now we've got a working graph. And you can adjust, you can play around with the settings a little bit, although that gets a little bit confusing here with what you're going to put in there. So maybe we don't go there right now. Maybe you just, you know, pan in and out a little bit, see if you can get that to work. Yeah, let's go to there. Okay, so that looks nice, and I'm pretty sure that's a straight line, right? So let's go ahead and transfer that information onto the graph that we have here, where we're going to put in our figure 0 had 1, 2, 3 tiles in it. Figure 1 had 9 tiles. Figure 2 had 15 tiles. Is that a straight line? Figure 3 had 21. Figure 4 had 27. And figure 5 had 33. Where are you, figure 5? What is that? 4 from the end had 1, 3, 2, 33. And now let's go ahead and make sure that that's a straight line. You may have noticed that I did something there and you're thinking I made a mistake, right? Well, sometimes I make mistakes on purpose to prove a point. It's like, oh goodness, which one am I supposed to go through? And so this is one of the reasons why you should plot multiple points from your table. Because if you make a mistake, see how if I go through this point and this point, I'm missing 3 others? Technically, I'm missing a 4th one up there because I'm sure that's not going to make it through. So it really looks like it's supposed to pass through here. And if I extend that even further, all right, so if my straight line using a straight edge or ruler passes through 1, 2, 3, 4, 5 points, but one of them it doesn't pass through, I'm really confident that this is the one that's wrong. So now let's analyze this one point and see where I might have made the mistake. And sure enough, I accidentally plotted it here instead of here. So let's go ahead and move that guy over. And now I know that I've got all my points in a straight line. If you were making mistakes and didn't know what you were doing, there is no way it would form a straight line. You would have them all over the place. The fact that you got 5 of them on a straight line and only 1 was slightly off means that you were on target. You just had to make the one correction. And now we feel pretty confident about that line. So now, what is the rule? What is happening here? It looks like let's see, here the rule looks like you would take x and add 3 to it, correct? But that doesn't work for any of the others. So that can't be the rule. Here it looks like x is adding 8. That doesn't work here, and it doesn't work there. So there's got to be some multiplication process happening here. So let me show you with the Desmos calculator how I can put in an expression, and I'm going to say y is equal to, let's just say, what would it be if it was x, ooh, y is equal to x, that's the line for y equals x, plus 3. All right, that's not our line, right? What if it was 2x plus 3? Okay, now it's starting to get a little bit steeper. What if it was 2x plus 5? Okay, notice how the line moved up a little bit. See this point right there? That's no longer on this one right here. So I think it's got to be, you got to have a plus 3 at the end there. So could it be 3x plus 3? Okay, we're getting closer. Now let's go back to the table for a second. What was the growth rate? How much was it going up by every single time? It was going up by 6, right? And so if you think back to the previous lesson when we were talking about the redwood trees, if it grew 4 feet per year, then, and x was the number of years, then the 4 became a multiplier, correct? So our multiplier was 4 times x. So I'm wondering if, in this case, since it's growing by 6, with every tile figure, it's increasing by 6, so maybe the 6 should be the multiplier, and we should put 6 times x plus 3. And look what it did. Our rule now matches up perfectly with our points from the table that we inserted. It's passing through every one of them. So your Desmos calculator can be a helpful resource for helping you figure out the rule, where you can do a little bit of guess and check and a little bit of maneuvering with this rule here. And once again, this is when you wrote the expression, f of x is, we'll get into that in a later chapter. That's another way of expressing y, but this is function notation. You don't know what that means right now, and that's okay. You'll learn it later. But this is what you would use to create a rule, and this is what you would use to create a table. And those two working in conjunction with each other can help you determine whether or not you've got the correct rule for this table of values. So as it turns out, you take a look at this, and the rule was y equals 6x plus 3. Okay, so let's go back and answer some questions now. First question, how many tiles will there be in figure 5? And we saw that there were 33 tiles in figure 5. And what would 100th figure look like? Well, 100th figure is going to have 603 tiles in it, right? Because you're going to multiply 6 times 100, since the figure number is your x in this exercise. 6 times 100 plus the 3 is 603. So that's, you would declare that answer. All right, now we've entered the information. What did we notice about, what was it? Enter the information for your XY table into your graphing calculator, then plot the points. What do you notice? You should have seen right away that if you had those figures correct, they would form a straight line. Now find another XY pair that you think belongs in your table and use your graphing calculator to plot the point. Does it look correct? How can you tell? All right, so let's go ahead and do that. What would be the next number in here? If we're increasing by 6, and the 6th figure should have 6 more than the 5th figure, so that would be 39. So let's see if that doesn't show up on our line, and it surely does. So we feel confident that it fell on the line, so it is correct. So imagine that you made 20 new XY pairs. Where do you think the points would lie on the graph? If you said you think they would all lie on that same line, then you are correct. Okay, so now something to be aware of. In a situation like this, where we're talking about figure numbers, is it appropriate to actually put that line onto the graph? Or is it better to leave them as individual points? That's where the next page is going to come into play. And I want to talk to you about the difference between continuous graphs and discrete graphs. Okay? So in the same window that contains the data points, graph the algebraic equation. What did you notice? It created a line, right? So the line went through all of the points. This is an example when you've got a line that passes through all the points. That is a continuous graph, okay? This right here is continuous because not only are all of the points in our table represented on this graph, but every infinitesimal point you can fit in between there also is on this line. That's the definition of a line. It's a collection of points that keep going on to infinity. So there are an infinity of points in between these 2 points, as well as infinity going to the ends of the universe for this particular line. So there are some situations where it's appropriate to connect the dots with a line, and there are other situations where it's not appropriate, okay? So if the graph of the tile pattern is continuous, what does that suggest about the tile pattern? That suggests you could have like a figure 1.5 or a figure 2.3. So do we have any figure 1.5s here? Are there any partial figures that we're trying to figure out? Or do we just go from figure 1 to figure 2 to figure 3 to figure 4? See, on the situation with John's giant redwoods, you could have measured the tree at any moment in time from the day it was planted, 50, 75, 100 years. So the decimal numbers or the fractional numbers in between year 1, year 2, year 3 had meaning in that particular context and was measurable. But are the fractional figure numbers in between these, do they have any meaning for this particular problem? And I would venture to say, no, it doesn't. So that's where the discrete graph comes into play. When you only plot the points, that's where you use a discrete graph, okay? So the figure numbers are only whole numbers, and none of the decimal numbers in between are represented, so we would not, in this particular situation, connect the dots. So going back to the graph, did I get rid, oops, stop it. Did I get rid of the line? Yes, I did. This would be the appropriate way to graph this particular situation, okay? So let me actually bring up a different example that I like to bring up with students to help make sense of this. Everyone's familiar with gallons, correct? When you go to the grocery store and you buy gallons of milk, you can only buy 1 gallon or 2 gallons or 3 gallons or 4 gallons. And if the price is $5 per gallon of milk, you're either going to spend $5, $10, $15, or $20, depending on the number of gallons that you purchase. But you can only purchase whole gallons. Please don't get into the whole buying quarts and whatnot. No, we're talking about the gallon jugs that you're going to purchase, okay? Now think of going to the gas station. The gas station is a continuous pump. You do not have to purchase 1 gallon or 2 gallons or 3 gallons of gas. You can purchase any decimal number of gallons. It's just this continuous flow. So if I was going to graph the possible gallons of gas that I could purchase at the gas station, I would want my graph to be a series of points I would connect with a straight line, because you could purchase any number of gallons. And here's my example. You could fill up your tank and it would take 15.47 gallons of gas. Well, you're not going to plot hundreds of thousands of individual points to represent every possible combination of gallons that you can purchase at the gas pump. So you just connect 3 or 4 points with a straight line, and you know that, oh, actually, let me pull this up, and you would know that all of the points in between are represented on that line, okay? Let me get rid of that line for this situation. We are only dealing with whole number figure numbers, so we want our graph to be discrete, okay? Hopefully that makes sense, the difference between the two. You will, in high school, I guarantee, be assessed on your ability to read through a word problem or any kind of problem and determine whether or not the graph for that particular situation should be continuous or should be discrete. It's being taught and introduced in 8th grade. I am not necessarily going to mark you down if you accidentally connect points, because I'll be honest with you, when I'm creating graphs, I often make the mistake. I just connect dots because I just feel like that's what the graph should look like. But then when I read through the problem, I realize, ooh, I shouldn't have connected the dots. It doesn't really apply here. So I have to erase. So do your best to get that right. The more we talk about it, the more it'll sink in when it's appropriate to connect the dots and when it is not, okay? There are even some situations where you're looking at it, it's like, is it appropriate to connect the dots and have an arrow at the end? Or would it be more appropriate to just connect the dots and not have an arrow, suggesting that that line would keep going on forever? Like, did we stop with figure 5? Could it have gone on to figure 6? Could there be an infinite number? Maybe we should have this line go on forever in that direction. Okay? Do we ever have a negative figure number? Does that apply in this situation? Probably not. So maybe we won't have the arrow going in the other direction. So there are a few different elements to graphing that we need to master. But this is all just being introduced to you right now. So, you know, we'll just build toward that, okay? Oh, why did I close that? I don't want to do that. I want to do this. Do I have any more problems to talk about? Okay, here we go. It says, for the following problems, justify your conclusions with the graph, the rule, and the figure, wherever practical, or whenever practical. Remember, this is a stoplight problem, so there's generally some mistakes, common mistakes that people make. Okay, so Angelica thinks that figure 6 has 40 tiles. Decide if you think that she is correct. How can we figure that out? Well, let's use the rule to see if we can figure this out. The rule said y should be equal to 6 times x plus 3. So, does figure 6 have 40 tiles? Well, let's see. 6 times 6 is 36. And then you add 3 to that. That's the 3 right there. And that gives us 39. So I would say no, absolutely not. Figure 6 doesn't have 40 tiles. It has 39 tiles. And let's go ahead and we can justify it with the graph. If I were to change this, change that to 40, and then let's go ahead and put in our line again. Y equaled 6 times x plus 3. And it's kind of hard to tell right there, but let me see if I can enlarge this a little bit. Enlarging it, come on, see how it's not falling on the line? So that's another way of proving. We checked it with the rule, but you can also check it with the Desmos calculator. 40 does not work. 39 was the appropriate number. Now it's falling on the line. Giovanni thinks that 0.1699 belongs on the table. Is he correct? All right, let's use the rule again. Let's say 99 should be equal to 6 times 16. This is terrible. Why are you not printing nicely? Hold on for a second. I'm going to do a little maintenance. I'll be right back. Okay, let's try this again. Let's see if 99 is equal to 6 times x, which is 16, plus 3. That's supposed to be 3. This is 96, and is 96 plus 3 equal to 99? Yes, it is. So we can say from our rule that he is correct. Now, if your graph isn't big enough, it's kind of hard to tell this with the graph. And the same thing with the table. That's what makes the rule, finding a rule, so beneficial. You can literally plug in any value for X and any value for Y in there, and then use your calculator, if necessary, to solve for the other variable, or to check whether or not Giovanni or Jeremiah or Frangelica or Latanya are correct. Okay? Jeremiah is excited because he has found another rule for the big C. Y equals X plus 8. Hooray! And your job is to prove or disprove that that other rule works. Well, I'm going to tell you right now, we're running out of time, so I'm going to just feed you the rest of this information for C and D. There's only one rule that can ever work for these situations. X plus 8 did not work for 0. Remember, one of the points on the graph was 0, 3. So when you take 0 plus 8, you don't get 3 for an answer. So that rule is absolutely wrong. It only works for 1, 9, only for this point. And Latanya has been thinking hard and has found another rule. She thinks that y is equal to 3 times 2x plus 1. Is she correct? And actually, it looks like it should be wrong because you can only have one rule, right? However, when you send in the dive bombers, notice what you get. 3 times 2x plus 1 is the same as 6x plus 3. So it turns out she is correct also. She has just rewritten the rule in a different form using distributive property in parentheses instead of having it simplified like we had it with 6x plus 3. All right, so play around with those decimals calculators. Get to use them because these will be a friend to you to make your job a lot easier as we move forward. If you can use these graphing calculators, use these online tools that CPM has made available for you. Okay, all right, good luck on the homework. Show your work. Please, when they ask you to graph, please take the time to graph. You need to be experts at graphing for you to be prepared for high school math when you go into 9th grade. Okay, take care, bye.
Hey, feeling good, like I should. When in dark, walk